Hello everyone, I'm Amir and today I'm going to talk about the project I did for this course CSC 579. The title of my project is speeding up route computation in traffic engineering using deep reinforcement learning. So I'm going to talk about the challenges of traffic engineering, existing solutions, and then our solution first. Then I'm going to talk about traffic engineering as a DRL problem and how we define our problem considering both link utilization and traffic rerouting. Then I will show you which programming language we used and which libraries we used in this to implement this project. Finally, I show you the dataset we use for this project and some results. In traffic engineering, it is challenging to react to the changes in network state quickly and efficiently. In SDN-based networks, linear programming approaches can be used by a centralized controller to provide the optimal solution for target functions, such as the multi-commodity flow problem in each time interval of traffic engineering. But the problem of linear programming approaches is that they are not scalable for big networks, and this is because computing the optimal solution using linear programming approaches is slow. The most recent proposed approaches for SDN-based traffic engineering schemes reduce the problem size of the linear programming approaches to avoid its long route computation time bottleneck. But the problem is that this reduction can have negative impacts on the accuracy and performance of the computed solution. For example, oblivious approaches avoid the overhead of running linear programming approaches in each time interval, but their solution is prone to mismatch the current or true demand matrix requirement in runtime. In oblivious approaches, when selected paths mismatch the current traffic demands or network state, oblivious approaches may suffer a performance penalty. So it's not useful to overlook some parameters to make it easier to solve the problem. So because of these problems, we consider deep reinforcement learning techniques to speed up route computation in traffic engineering. DRL is a subfield of machine learning that helps an agent to learn to achieve goals in a complex, uncertain environment. We investigate DRL for online route computation tasks in traffic engineering. Here in figure 1, you can see a big picture of how a DRL agent interacts with the environment for traffic engineering tasks. Depends on the target function. The input to the learning model can be any subset of the inputs, including network topology, link failure probability, and so on. For each state, the DRL agent takes an action. And once the agent chooses an action, it receives a reward, which is a numerical value that shows how good or bad the chosen action was. Since the training phase happens offline, we can use linear programming approaches to evaluate the chosen action by the agent. And the goal of the agent is to learn a mapping from the set of possible states to the space of the actions that maximizes the expected reward that it receives from the environment. So our scheme uses DRL to speed up route computation as follows. Given the current network topology and other possible inputs, such as device matrices, demand matrices, our DRL agent identifies a subset of flows in the network that is required to be rerouted in the network in order to optimize the target function. And considering the fact that demand matrix varies in the level of minutes and the network topology can change at any time, it's hard to quickly and efficiently identify this set of flows using linear programming approaches. For example, if we want to identify 10 flows among 100 flows, the solution space has 17 trillion combinations, which using the linear programming approach is not reasonable here. So one of the advantages of our scheme is that it's learning this solution offline and computes the solution for different target functions quickly online. So how do we evaluate our scheme and results? We evaluate and compare our approach to other traffic engineering schemes that use linear programming to solve the optimization problem. First, we show DRL can be used to avoid rerouting many flows in each traffic engineering time interval effectively without sacrificing link utilization too much. When the maximum link utilization in the network is low, our scheme avoids rerouting a large number of flows in the network. However, it's increasing the number of suggested flows when it's necessary. And by using DRL, we want to find the balance between availability and throughput in the network. And this helps us to reduce routing for around 30% of the flows in the network at each time interval on average, without sacrificing the link utilization too much. So we want to answer this question that how using DRL lets us to reduce the traffic fluctuation in the network without sacrificing too much of link utilization. We define traffic fluctuation as the number of flows that are required to be rerouted in the network in each time interval. So it's reasonable to avoid rerouting a large number of flows in the network when the variation in the traffic demand is not high regarding the demand matrix in the previous time intervals. So which means that we need to try to avoid do a lot of rerouting because it increases the traffic fluctuation. So in this case, we can use the established tunnels from the previous time intervals for spending the traffic of most of the flows. By sacrificing the link utilization value, which means going beyond the optimum value by a control threshold, a traffic engineering scheme can reduce the cost of using new paths and avoid traffic fluctuation in the network. So in a nutshell, if I want to tell you is that we want to make a trade-off between maximum link utilization and the rerouting cost here, and we want to minimize both of them at the same time. So maybe sometimes to minimize the cost, we need to increase the link utilization a little to make this trade-off. But at the end, we minimize the sum of both of them. The problem that we use DRL to solve in this section is as follows. Given network topology and demand matrix in k previous time intervals and the demand matrix for the next time interval, we want to see what are the minimum number of flows that are needed to be routed in the network in order to achieve max link utilization. So we call this set of flows deciding flows. The size of this set of flows can be different for each different states of the network. And after identifying the deciding flows in the network, we compute the sending rate on links for them using linear programming approaches. The traffic of other flows will be routed based on equal cost multipath routing or ECMP approach or via established tunnels in the network in the previous time interval. So the main parts of our deep reinforcement learning model are input or a state space, action space, and the computing reward. For the input or a state space in our approach, a DRL agent observes a set of metrics including previous K demand matrices and previous K intervals, network topologies, and the demand matrix for the next time interval. And for the action space, for each state, the agent would feed the value of the previous parameters to the neural network and outputs the action, that is the set of deciding flows to be routed in the next time interval. And for the computing, reward computation, for each set of flows suggested by the DRL agent, we compute the maximum link utilization after rerouting the suggested flows in the network and compute the reward using this equation, the equation that you can see here, when the maximum link utilization for DRL is less than or equal to this value, and we set the reward to a very small value when the MLU of the DRL is larger than this specific value. So for the implementation for the pre-processing and the implementation of our deep reinforcement learning model, we use Python programming language. For the machine learning part, we use TensorFlow libraries. But for the to process our data and analyze our data before we use that as the input in our machine learning model, we use libraries like Pandas, NumPy, NetworkX, SciPy, and some other Matplotlib and some other libraries to process our data and extract the main parts of the data set. We consider a three-layer neural network model. The first layer is the convolutional network, convolutional neural network with 128 filters. We consider the kernel size as 3 by 3 and the stride as 1. We consider the fully connected layer with 128 neurons as the second layer. For the first two layers, we consider the Lickey-Relu for the activation function, and we considered a fully connected linear layer as our final layer. And to generate the probabilities for all available actions, the softmax function is applied upon the output of the final layer. So for the evaluation in this section, we first show that DRL can be used to avoid rerouting many flows in each traffic engineering time interval effectively without sacrificing link utilization too much. We then show we can increase the availability and throughput in the network using DRL in comparison to other basic approaches, such as routing the traffic using equal cost multiple pass or ECMP approach. The data set that we use is the data set belongs to ATT network routing topology. ATT network has 25 nodes and 112 links. In our data set, we have 200 traffic matrices, and each traffic matrix has 600 flows, and each traffic matrix file has 67,200 rows and 7 columns. And the main thing that we try to extract from this data set was the different paths for each flow, and also the maximum link utilization, the optimal maximum link utilization that we calculated before using linear programming approaches. And then by finding the different paths for each flow, we add the paths used frequently for each flow into action list and use that action list and the network topology and the optimal maximum link utilization as the input of our deep reinforcement learning model. Then we calculate the maximum link utilization of the DRL, compare that to the optimal maximum link utilization, and calculate the reward. So for this purpose, we use the 70% of the data set as the training set and 30% of the data set as testing. In the first evaluation, the goal of this experiment was that to show that our scheme reduces unnecessary flow rerouting without sacrificing the link utilization in the network. As you can see in figure 2, it shows a CDF on the number of flow reroutings for all tested states in the network for our scheme and linear programming approach. We have plotted the results for our approach with 1,000 and 2,000 epochs in the training phase. And as you can see here, DRL is able to reduce the number of flow reroutings in the network without sacrificing the link utilization too much in compared to the linear programming approach. We need to reroute around 50 new flows in the network on average for each time interval when we are using linear programming approach, but this value is around 35 for the DRL approach. Here in figure 3, you can see that the average maximum link utilization in the network for 100 tested states for different schemes as a function of demand scale. And as you can see here, the linear programming approach can provide the minimum link utilization in the network. But in figure 2 here, you can see that more flows need to be rerouted in the network for each time interval when we use linear programming approaches. So in linear programming approaches, they don't consider the rerouting cost. So because of that, they can reroute different flows to get the minimum maximum link utilization. But when we use DRL, we want to minimize the rerouting of the flows. So maybe we cannot reach the exact minimum maximum link utilization, but we can reach the near optimal minimum maximum link utilization. So yeah, oh sorry, I forgot to change. Change the slide. Yeah, I explain here this part again. As you can see here, in figure 3, the linear programming approach can provide the minimum link utilization in the network, but this is because the linear programming approach doesn't consider the rerouting cost in its computations. So that's why it can reach the minimum maximum link utilization. But more flows need to be routed in the network for each time interval when we use linear programming approach in comparison to the DRL, as you can see in figure 2 here. But the main reason that we don't want to reroute a lot of flows because that rerouting flows is not a cheap process. So here in figure 4, you can see the value of throughput in the network using our scheme for different target values of availability. DRL can help to send more traffic in the network for target availability in comparison to the ECMP approach. So as you can see in this figure, while the throughput of the network using the linear programming approach is higher than our scheme provides this level of throughput by only rerouting 20% of whole flows in the network. So again, I need to mention that linear programming approach only wants to minimize the link utilization, and it doesn't consider the rerouting, traffic rerouting cost. But here in this work, we wanted to consider both linear link utilization and traffic routing cost at the same time, and make a trade-off between them, and minimize the sum of both of them. So because of that, maybe if we want to do less rerouting, we need to increase the link utilization a little bit. And in this work, we attempted to enable DRL for 2 different target functions of traffic engineering in the network. We deployed and evaluated our approach on a real test bed and demonstrated its performance and adaptiveness to traffic demands for ATT real network topology and its datasets. Our schemes uses modern reinforcement learning techniques to learn from the actual performance of past choices to optimize its control policy for traffic engineering decisions. A huge benefit of our approach comes from its ability to limit rerouting many flows in the network over time and making the decision quickly without having to solve a linear problem in each time interval. In different experiments, we are able to show that our approach performs better than classical approaches such as ECMP routing and can achieve the near optimal solution. So thanks a lot for listening to my presentation. And if you have any questions, you can ask me in Bright Space. Yeah, thanks a lot. Thank you very much.